Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of scientific discovery, the year 1938 stands as a pivotal moment, marking the conceptualization and initial theoretical explanation of nuclear fission by Lise Meitner and Otto Robert Frisch. This intellectual breakthrough, revealed in their seminal paper, fundamentally reshaped our understanding of nuclear physics and, indeed, the very fabric of matter. An exploration into the genesis, scientific underpinnings and enduring legacy of this work reveals its profound implications, extending from the theoretical realm to practical applications that continue to shape the intellectual landscape preceding 1908 was rich with experimental and theoretical developments in nuclear physics. Ernest Rutherford's groundbreaking work on atomic structure, culminating in the discovery of the atomic nucleus, laid the foundation. His experiments, involving the scattering of alpha particles by gold foil, demonstrated that atoms possess a dense, positively charged core. Niels Bohr's subsequent model of the atom, incorporating quantum mechanics, provided a framework for understanding atomic behavior and spectra, although it did encounter certain limitations, particularly in explaining complex atomic spectra and the nature of the nucleus itself. Further progress came from the experimental investigations into artificial radioactivity. Ian Joliot-Curie and Frédéric Joliot demonstrated that certain elements could be made radioactive through bombardment with alpha particles, opening up entirely novel avenues of exploration in the field. Enrico Fermi and his team in Rome systematically bombarded various elements with neutrons, leading to the discovery of numerous new radioactive isotopes. Notably, their experiments involving uranium produced puzzling results, with observed activities that defied straightforward interpretation based on existing understanding of transuranic elements with an atomic number higher than that of uranium. These observations from Fermi's uranium experiments stimulated intense debate and further investigation within the scientific community. The prevailing hypothesis suggested that the neutron bombardment created elements heavier than uranium, that hypothesis being transuranic elements, fitting neatly within the established periodic table. Otto Hahn and Fritz Strassmann, in Berlin, meticulously attempted to isolate and characterize these supposed transuranic elements, only to encounter an unexpected chemical anomaly. Their rigorous chemical analysis revealed the presence of barium, an element significantly lighter than uranium. This discovery presented a major paradox. How could uranium, upon neutron capture, transmute into barium? This defied all existing theories of nuclear transmutation, which posited small changes in nuclear structure through the emission of alpha or beta particles. Lise Meitner, a physicist of immense talent and experience, had collaborated with Hahn for decades, contributing significantly to the discovery of protactinium. However, due to the increasingly hostile political climate in Nazi Germany, Meitner, being of Jewish heritage, was forced to flee to Sweden in 1938. Despite her physical separation from the Berlin laboratory, she remained in close intellectual contact with Hahn, constantly engaging in correspondence to understand the ongoing experiments and their implications. It was during this period of exile that Hahn shared the perplexing results concerning barium with Meitner. Initially skeptical, Meitner pondered the experimental evidence with her nephew, Otto Robert Frisch, also a physicist. Frisch had travelled from Copenhagen to visit her during the Christmas holidays. Together, they critically examined the experimental data and attempted to reconcile the seemingly contradictory chemical findings. The crucial insight came from considering the liquid drop model of the nucleus, proposed by Bohr. This model viewed the nucleus as a charged liquid drop, held together by nuclear forces, that exhibited surface tension. Meitner and Frisch realized that the absorption of a neutron by the uranium nucleus might cause a destabilization, inducing the nucleus to elongate and eventually split into two smaller fragments. They calculated the energy released during this process using Einstein's famous mass-energy equivalence formula, E=mc², where E represents energy, m represents mass, and c represents the speed of. Their calculations revealed that the electrostatic repulsion between the positively charged fragments could overcome the nuclear forces holding the nucleus together, resulting in a tremendous release of energy. Specifically, the mass of the original uranium nucleus was slightly greater than the combined masses of the resulting barium and krypton nuclei, with the difference being converted into kinetic energy according to E=mc². This calculated energy release, approximately 200 megaelectronvolts, was significantly larger than any previously observed nuclear reaction, explaining the immense power potential of this newly discovered phenomenon. Meitner and Frisch coined the term nuclear fission, Drawing an analogy with the biological process of cell division, Frisch then returned to Copenhagen and informed Bohr of their theoretical interpretation. Bohr, upon hearing the explanation, immediately recognized its significance, exclaiming, "Oh, what idiots we have been, but this is wonderful. This is exactly as it must be." The rapid dissemination of Meitner and Frisch's findings had an immediate and profound impact on the scientific community. Physicists around the world swiftly began to confirm their results experimentally. Within weeks, numerous laboratories had replicated the fission process, measuring the energy released and identifying the fission fragments. It became evident that nuclear fission was not unique to uranium but could also occur in other heavy nuclei, such as thorium. One of the most significant implications of nuclear fission was the realization that the process also released additional neutrons. This opened up the possibility of a self-sustaining chain reaction. For every neutron absorbed by a uranium nucleus, more than one neutron could be released during fission, potentially triggering further fission events. If this chain reaction could be controlled, it could provide a vast source of energy. If uncontrolled, it could lead to an enormously powerful explosion. This revelation spurred intense research into the feasibility of nuclear reactors and, tragically, nuclear weapons. The outbreak of World War II accelerated these efforts, with the United States, Britain, and Germany all initiating secret programs to explore the potential of nuclear fission for military purposes. The Manhattan Project, launched in the United States, ultimately succeeded in developing the first atomic bombs, forever altering the course of history. The discovery of nuclear fission also had a transformative effect on the field of nuclear physics. It stimulated a wealth of theoretical and experimental investigations into the structure and behavior of atomic nuclei. Scientists developed more sophisticated models of the nucleus, refining the liquid drop model and incorporating quantum mechanical effects. The study of nuclear reactions became a major area of research, leading to the discovery of new isotopes, new elements, and novel forms of radioactivity. In the aftermath of the war, nuclear fission technology transitioned from military applications to civilian uses. Nuclear power plants were constructed around the world, providing a significant source of electricity. While nuclear power offered the promise of clean energy, it also raised concerns about safety, waste disposal, and the potential for nuclear proliferation. These concerns continue to be debated and addressed today, highlighting the enduring social and ethical implications of Meitner and Frisch's groundbreaking discovery. Despite her crucial role in the discovery of nuclear fission, Lise Meitner was overlooked by the Nobel Committee when the 1944 Nobel Prize in Chemistry was awarded solely to Otto Hahn. This omission has been widely regarded as a significant injustice, reflecting the gender biases prevalent in science at the time. Meitner's contributions were fundamental to the theoretical understanding of fission, and she deserves equal recognition for this groundbreaking achievement. The legacy of Meitner and Frisch's 1988 paper extends far beyond its immediate impact. Nuclear fission continues to be a vital source of energy, powering nuclear power plants worldwide. The principles of nuclear fission also underpin nuclear medicine, enabling the diagnosis and treatment of various diseases. Furthermore, the study of nuclear fission has contributed to our understanding of the fundamental forces that govern the universe, advancing our knowledge of nuclear structure and reactions. The intellectual lineage stemming from this work is substantial. For instance, the liquid drop model of the nucleus, employed by Meitner and Frisch, evolved into more sophisticated models incorporating shell structure and quantum mechanical effects. These models, such as the Nielsen model, enable physicists to predict and understand the properties of nuclear isotopes, which are critical in applications ranging from nuclear astrophysics to the design of nuclear reactors. The very mathematics needed to analyze fission, such as differential equations describing nuclear potential, became the focus of intense scrutiny, leading to advances in asymptotic analysis and computational techniques. Moreover, nuclear fission spurred the development of new experimental techniques for studying nuclear reactions. These techniques, including heavier ion accelerators and sophisticated detector systems, allow scientists to probe the nucleus at extremely high energies. This advanced technology is crucial for exploring the limits of nuclear stability, discovering new elements and synthesizing exotic isotopes. The understanding of nuclear fission has also influenced our comprehension of stellar nucleosynthesis, the process by which elements are created inside stars. Nuclear fission plays a role in the termination of stellar cycles and in the production of heavier elements in supernova explosions. Meitner and Frisch's discovery, therefore, has had a lasting impact on our understanding of the cosmos. The discovery of nuclear fission, while celebrated for its contribution to science and technology, also faced significant critiques and revisions. Early models oversimplified the complexity of nuclear behavior, leading to inaccuracies in predicting fission probabilities and fragment distributions. These initial shortcomings spurred a rapid development of more sophisticated theoretical frameworks, including the incorporation of quantum mechanical tunneling and statistical models. Such advancements provided a deeper, more nuanced understanding of the fission process. Societal reception of nuclear fission has been complex and multifaceted. The devastating use of atomic bombs during World War II created a deep-seated fear of nuclear technologies. This fear persists today, influencing public perceptions of nuclear power. Efforts to promote safe and responsible use of nuclear energy continue, balancing the need for clean energy with concerns about nuclear proliferation and environmental risks. The 1958 publication by Lise Meitner and Otto Robert Frisch stands as a testament to the power of scientific collaboration, intellectual curiosity, and the relentless pursuit of knowledge. Their meticulous analysis, groundbreaking theoretical interpretation, and clear articulation of the nuclear fission process revolutionized physics and profoundly impacted society. This work serves as a potent reminder of the enduring legacy of scientific discovery and its ability to shape the course of human history for both beneficial and challenging eventualities.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.